integrated the monotype and the synthetic. And usually we consider the propagation speed of the electromagnetic waves, and it is usually increase space, so it is the speed of light. There's the power h meters per second. So even though the received signal consists of the sum of the echoes from the different areas within the antenna range, and the range, and also the government information mixing the phosphor substrate on this range. So really we use the range discrimination and use the double shape discrimination to achieve our recognition of the object on ground or on terrain. So here is the first thing we should introduce is the CW radar, and the CW course the continuous radar. So it is a simplest radar, right? And we firstly consider our target is a stationary target relative to the radar. So that means if the radar moves, the target can move in the same direction and with the same speed, or if the radar is fixed, the target will also be fixed also. On the right, so here is a diagram for the radars. The first one, you can see it has a transmitter and also a receiver. The second one, it has the transmitter and its receiver are integrated. So it has a new antenna for the detection. So the first one we call it a bistatic configuration. And the second one should be monostatic. So the bistatic means it has two antennas, and the monostatic means it has one antennas. So for the first one, here, the transmitter, the CW oscillator and amplifier, and then radiated from all from the antenna, and each interacts with the target, and then reflected back then the receiver, and here there is a mixture which combines the received signal and part of the transmitted signal, or a copy of the transmitted signal, and to do the downversion. So and the amplifier and the processing and display. And the same thing for the monostatic configuration also. The only difference for both is the coupling. So because we have one antenna in the monostatic configuration, so the most important thing to look at is how to separate the transmitting signal and the receiving signal collected by the same antenna. So this is a little bit difficult thing here, but it has one advantage over the bistatic configuration is that because it employs only one antenna, so its volume of its weight is much more than this one, because it has two antennas. can reduce it to be half of that, then that means the volume of our whole system will reduce significantly. Here, if we want to express how the signal propagates or the signal performs, we need to design the signal at the transmitter side. So here, we define Vt as the transmitter side, the signal voltage at the transmitter side. So we regard it as a cosine function, and A as its amplitude, and node is frequency, right? So, and T equals to R divided by C. That means T is the time delay due to the reflection by the target. So because the distance between the antenna and the target is only R, so here we can propagate and then come back. So it has to run laterally and back and forth. So it's 2R divided by C, speed of here, alright? But for the biset configuration, sometimes the antenna and the transmitter and the receiver at different positions or different locations, and they both have a distance, so the RT and RR should be instead of 2R, the RT plus RR. But surely the RT or the RR is much larger than the distance between both antennas, so both can be regarded as 2R also. So now at the receiver side, so everything clear, alright? So there's no noise, there's no other noise, there's no disturbances. The receiving signal, VR, right, should still a cosine function, and its frequency is at node. But there is a phase difference, right? The phase difference is due to the propagation distance from the transmitter to the target and then back to the receiver. So it's related to a constant T here, capital T, and a K. So previously A is the amplitude and the transmitter side. K should also be an amplitude and the receiver side, right? So it should be include the what? Should include several parameters. The first thing is the reflection by the target, right? Because it propagates, it's locked onto the target and then reflected back by the target. So it should be related to the cross section of the target, right? Onto the electromagnetic beam. And also it's related to the gain of the antennas, the wavelength, also the distance. Alright? So here P, that means the amplitude and the receiver side. And the phase shift, as previously mentioned, it equals to pi omega capital T, alright? The time from the antenna to the target and back to the antenna. And the T can be finally expressed by this term. So this is a phase shift. And here should be Vt. And Vt is here, Vr is here. So after a mixing, as the previously mentioned, the mixture can achieve the down-conversion of the signal back to the baseline. So, how it works? From this configuration, it mixes a copy of the transmitted signal, alright, the synthetic oscillator, and also the received signal from the antenna. So A equals Vt times Vr. So Vt can be expressed by this one. Vr can be this one, right? The multiplication of both terms. And then we have a cosine at node t times the cosine 2 pi at node minus 1 here, the base change or the base shift. And then for cosine alpha, cosine beta, we express it as half cosine alpha plus beta times half cosine cosine alpha minus beta. So we get both terms. This one plus this one minus. So now the multiplication of both terms can be simplified to be two terms, right? The first term is the sum, and the second term is the difference. So if we want to consider both terms, previously we can see here for this one, for this term, its carrier frequency is how much? Its carrier frequency for real at node, right? Its carrier frequency is at node. So for this term, its carrier frequency becomes double at node. And also another term is 5. So if we set a low pass filter, we use a low pass filter here, and we then erase this term, and we only collect this term, right? So our output becomes this term. And because if the target is fixed and the real system is fixed on its position, so the distance between both we always r is a constant, right? So r is a constant. So that means the output we know should be the DC component, right? So it should be a constant. However, if the subject, for example, it has its position varies, that means we know should also vary, right? So here we can, based on this equation, we can obtain some information about the object. Also, the amplitude is determined by the transmitted power, the transmitted amplitude A, and the received amplitude K, right? Because K is related to so many parameters, right? For a given system, its gain is fixed. Its transmitted amplitude is fixed. Its wavelength is fixed also. The only term is the cross section. So here we can obtain then if we know the distance from the radar system to the object, we can obtain the cross-section by the backscatter signal and mirror, as we know. So then obtain the cross-section here, and as we introduce the loss rate, if we know the cross-section, we can get some information about the object, such as its dielectric constant, alright? And also sometimes we get the size or its shape or its surface properties, such as its roughness, and many parameters that we can obtain by set backscatter cross-section from the data system. So, when we back here, now we can obtain our received signal by this one. So, based on this one, we note a simplest model to express how the radar signal propagates in brief space due to reflection by an object. So here, if we change the distance between the object and the radar system, the output amplitude will vary, right? So because the cosine function varies from -1 to 1. So the output amplitude varies from -80 over to positive 80 over 2, corresponding to a change of lambda over 4, right? For example, if it's positive, that means lambda can be how much? No, okay? If we change it to lambda to be lambda over node over 4, that means the variation of this one there is a variation of 1, right? 1 over 1, 4 over 4 equals 1. So that means it becomes a minus positive value. For example, at x band, the lambda is 3 centimeters. So it will lead to a change in the R at around 0.75 centimeters. That means if we use x band radar system, even if receive of the collective amplitude by the receiver varies from a positive value to an activated value based in absolute value, then it can be achieved only when the distance varies for around 0.75 centimeters. So that means if object moves, right, 0.75 centimeter, at the receiver side, our detector or our receiver collected the signal varies significantly, right, from positive to a negative value. So that means the radar system is very sensitive to the position of object, or is where it can achieve a range discrimination. So, synthetic radar is a very sensitive instrument for measuring changes in R, but cannot directly measure R itself, alright? Because there is a cosine function. So, at one determined value, there should be several values for R to achieve the same one, alright? To achieve that. So you cannot directly measure R itself. Sometimes we use using, for example, American methods, but American methods can only be used only But we take our reference from the beginning point, that means from the antenna side, and the involved it collects every values at 8 positions, and then using the array method or array algorithm to achieve or to correct the values. But here, for radar measurements, we cannot achieve such detection. So we need to know or to find some other methods to do that. Here, for signal scintillation. So if we consider we have two targets. Okay? So the first target is here is target 1, and here is target 2, and our radar here. So they receive the signal, the distance from the antenna to the radar to target 1 is R1, target 2 is R2. And D1 equals to R1 divided by C. D2 equals to R2 divided by C. So our collected signal should be the received signal by the antenna should be V1 and V2, alright? Because previously we just mentioned that our target is just a point or a pointer. But actually, our target should be has a distribution, right? So if target 1 and target 2 are the same target, that just means there are different positions, and we regard each of that as target 1 and as target 2. And the distance between both should be smaller distance. D is much smaller than the distance from the radar to the target. So here, our received signal should be this one and this one, right? So if we have two signals comes to one point, and the both components are in phase, that means there should be what? There should be what? If two signals comes to one point, and both are in phase, they should interfere, right? Because they are incoherent. So they should interfere, and they should combine to be just one component. How we can achieve that? If we have two components, this is R and this is beta, and they are in its, it should become to be as one, right? So here, because the rest elements R1 is much larger than D, so R1 can be expressed as E naught plus B over 2 times sin theta. Here is beta, so this one is beta also, and this term here is beta also. So this term is plus, here it's minus, so you can get each express substitute on and multiply from the and E. And finally, becomes becomes this one, and then it becomes to be this one. So this is the window out. So here, if the distance from transmitter to the object or node is constant, and this charge is constant also, and it can be the y to be amplitude, and here is the variation. So the magnitude of the baseline voltage should be like this one. Right? Let me come back to this one. For a point target, like this one, also for one target, it has no difference. There is no difference for the incident angle, alright? This is because that's only one point. This collects the signal from over longer should be the same received reading signal, but here the incident angle is theta. If theta changes, the received signal should also vary, right? So that means the measured voltage or measured power varies with respect to the incident angle. So that's why for the reading systems, you want to use that. The incident angle should also be a very important parameter. Alright? And also the incident angle would what? Would affect reflection or reflectivity by the target or by the object. Alright? So the incident angle is very important. Here, previously we said the target is a stationary target, but for a moving target, then very common parameter which we regularly know is the Doppler frequency shift due to the relative movement between the object to the antenna or to the radar system, alright? So a Doppler shift is named FD shift or Doppler frequency shift. So here, if we want to see how the CW system moves, the instance frequency of the same wave and the time derivative of the argument of the same wave conducted, right? So previously, we know that the frequency or the phase component of the received signal V like this term, right? This term. So this is 2 the F node. T minus F to R divided by C, right? So if the phase shift, that means the received signal voltage or the received voltage varies with respect to time. So if we take time derivative onto this term, we can get a frequency component like this. So the time derivative is a node at this part. So if we look at this term, we convert it into frequency, now angular frequency, and it becomes this one, alright? So it has 2 terms. The first term in that node is the original frequency of the signal, and it has another term, right? because the object moves. That means the distance between the object and the relay system varies with time also. So it is time derivative on this branch. And we name it as FD. So FD is defined by this term. Okay? So here we define the time derivative of the distance between the object and the relay system to be the Doppler frequency shift. Because object moves, it should have a speed, alright? So we need to convert it to the speed or velocity of the object. Here we define the R or dt as UR, smaller case UR. So UR is the relative velocity between the radar and the target in the radial direction. Okay? In the radial direction. So if that means it moves to the relay system or moves away the relay system, and both are in a line, right, or moves along a line. But however, if our relay system moves along this direction, but the target moves along this direction, both have inverse curve, that means UR, the relative velocity should be converted to U times cosine R, the speed of the relay system times the cosine the angle between the movement of target and the relay system. So this way. So the Doppler frequency shift term becomes like this one. Here we need to here S. So UR should always a positive value, alright? The speed or velocity should be always a positive value, alright? Our frequency should first be a positive value. Alright? Our frequency should also be the double frequency should also be positive value. But why there is minus sign in this equation? Why? It's because UR is larger than 0 when the radar moves to the object, or object moves to the radar. That means their distance becomes closer, right? Both the transmitter and receiver. So if it's it's larger than 0 means the relay system is away, or the target is away the relay system, and then it is more than 0. That means the target approaches the relay system. So when the target approaches the relay system, if R is more than 0, then this term is positive. That means the Doppler frequency is not zero, that means the target is away from the object, away from the radar system. So that means the frequency is negligible, and the detected frequency component or the detected frequency is becoming smaller or is decreasing due to the problem shift. Alright? So this is why there is minus sign here. So we want to assume that we want to express that in a collision coordinate system and x or y date. So assume the radar moves along x-axis. The radar moves. So radar system. So its velocity can be expressed by the unit vector x, right? And our object or target is positioned at x, y plane on the x or y plane. So it's positioned in x, y node. Okay, then this and the radar. Now, when the radar moves onto the data axis, and the height is h, right? So the distance between the radar system and the target becomes x, y, and the radar components, right? Here I showed the direction of this parameter is from the radar system to the target. So x equal to y equal to what data to match on this direction. From here to here. So this is our yes. So the FD can be expressed by this one. So it becomes the approach frequency shift becomes like this. H is depends on the velocity of the radar system, also the position of the radar system and the target. So isotopes. Actually, isotopes means what? Means we can get the same values of the same frequency values from the object, but in the same collision coordinate system. So that means along this line, in this line, the hit point, you can get the same approach and the same frequency. And along this line also the same thing. Along this line also the same thing. And along this line also the same thing. The circle or the circle area is the illumination area or the illuminated area on the object for the radar system. So there are so many lines. For the opposite line, that means we can get the same voltage or the same frequency components. That means we can note this coordinate, the object or the small objects, the points on this on the same line, right? So for approximately band phosphor rate received signal, we can separate the region from one area and another area by what? By the pattern and the frequencies that will form in the band phosphor. So So by different frequencies. So, for example, if for sound looking radar, so this is the sound looking antenna pattern here. Then the radar system moves along the x-axis. So for it, its ice Doppler controls like this one. So for the 2 points in the same on the same line, the radar system cannot separate it. But for different lines, they can describe why the difference. So this is the ourselves, which will be used later in branch informed resolution of the radar system. So, as we already know that our radar systems sometimes can be CW and also can be pulse radar, right? They are most commonly used for the most simplest radar operations. A CW radar transmits and receives continuously. However, it can transmit and receives continuously that it will lead to some disturbance by onto the receiving signal by the transmitting signal, right? If we use a pulse radar, we set a pulse radar and they come back, and we receive that, and then we set another pulse, and then they come back, and then we set a third one. So there to be always no interference between both, alright? Both pulses, because we set another after we receive the former one. So pulse radar can be used to reduce the interference of the signals of itself. But for our pulse radar, the pulse length, the length of it, or the frequency of the pulse repetition frequency, the proportion of the pulse length, right? Or the length for its period. And also the separation between two pulses. The pulses
let's just take a short break. And if you are not interested, you can just go back to office and just videos. 如果没啥兴趣的话，可以回办公室，然后看视频。这节课没有 checking。
So, possibly, if assessment reports the latest one and one this month, right? And the received signal becomes like this. It's a little bit different from the first one because PT, we use the PT to describe how the pulse. We do not use the cosine function, right? Because now it's pulse reader, not a signal reader. So we use PT to describe a pulse, and if there is time delay, capital T here, and also it's AT. And also there is a factor that contains all the system and propagate and tension parameters. So you combine all these parameters together and represented by the wire AT. So if there are many steps on the object, so we should clean influence some of that. If it's not a plan, but a distributed target becomes like this. So now, if it's not a point target, there should be a resolution or a discrimination of each one. So how we could describe or recognize two different targets separately or respectively. So this is related to a range discrimination. So for example, if we have a house set out, we have another house, right? If the time separation between two houses is very long, that means we need more time for target detection. But if their separation is very small, then they're going to affect or they're going to influence or they're going to degrade this resolution. So, for example, if at time t1 the pulse probably to a position like here, and at time t2, so it raised to the target 1 and comes back a little bit, right? So let's start a return starting from target 1. And at t3, a return also starting from target 2, right? So the right dashed lines correspond to target 1 and target 2 at this position. And at time t4, here, there is no return from target 1, but there is return from target 2, right? And at time t5, there are no returns from both objects. So that means at t2, we have superposition, we have return or feedback or reflection by target 1. And at t3, we have back reflection by both targets. And at t4, we have the reflection by the target t and target 2. So that means on the receiver side, we have superposition on overlap of reflection by objects. And our detection cannot recognize both pulses from both here. So we only collect a much longer pulse. So that means there is no separation between reflection by the targets, and we cannot recognize that. Okay. However, for this one, we can see when the reflection from target 1, there reflection from target 1, then there cannot achieve reflection from target 2. And when there is reflection from target 2, there is no reflection from target 1. So on the research side, the target 1 and target 2, there is a gap between both. So that means both objects or both targets can be recognized or can be discriminated by such pulse related notion. So that means the discrimination capability is related to the duration of the pulse relative to the spacing between two targets. Alright? So this can affect the range discrimination of our relay system. The same thing, if we define such as the target line of the relay system is R1. So the end is the end of the pulse. We send from the first target here. But the start of the pulse return from the second target, there's no total, right? Because it's related to the start of the pulse return. So if we want there is a gap or separation, that means the time from this one TA and from TB should be larger than TB, right? That means the first pulse, the pulse from the first target comes back, but it still cannot arrive at target 2. So TA is larger than TB. That means there should be a separation or there should be a gap between both targets. But the critical point is TA equals TB, alright? So the critical point is this one. And then from here, the distance between R1 and R2 difference for the R becomes this term. This is called the range resolution. So this is the definition for the range resolution of the relay system. And if the pulse length is 1 nanosecond, the range resolution can be 15 centimeters. If it's 50 seconds, should be in the microwave, right? So range resolution. Okay, actually, previously here we said pulse with launch out is a square wave. Actually, if we want to send out the square wave on the Fourier transformation, there should be infinite number of cosine components, right? All the same components, which very much power consumption. So for actual pulses, where we left out should be a Gaussian pulse strip. In a Gaussian pulse strip, like this one. So now, this should be better, right? If for a survey, there will be a electrical position with a significant reduction in the discrimination, but for the pulses, small position, there seems to be some calculation like this. The total of that maybe looks like this one. There is a deep. So, based on this one, we can also describe they all recognize both targets. Under the condition that the noise cannot emerge such a separation. If the noise level is very large, that even though there is more dip, but it is more in the noise, then we can still also cannot recognize that. And then the separation is larger. Then it's easier for us to recognize that. And also here, there is knob. Right there is knob. That means any conditions, we have all these very knobs of purpose. So here, isolated construct again. As we machine. The return signals from the targets at different ranges or time delays can be separated based on the cross shape and length. So these isometric lines define regions of surface that generate written signals received by the radar at the same time. So for these circles, for points that in one circle is the outpost, the time delay detected by the radar should be constant. So the written signals from these different regions within the footprint can be separated by time varying the data and looking at the radar within a short time window or gauge. So the separate variable is known as the range gauging. So the range gauging can be used to define how the user can explain the regions of the objects of the initial area. The range gauge enables the radar to show targets at different ranges. So at different ranges, it would be in different lines or along different lines, and you can get a different delay and separate the difference. We can recognize the difference between targets. So how we could define a resolution, right? So how we could know that the separation of both targets can be recognized, and how we can think it cannot be recognized. So there is a term called half power bandwidth. Previously we know that there is a term called half power bandwidth. So that means half power is usually evaluation parameter of that chart in the power, amplitude, and in many figures. So in microwave sensing, the resolution is the spacing between the points at which the response power is half the peak power response. So that means for a Gaussian line parsec, the resolution is measured at half power point. So if the peak power is dB, then the half power point should be at the position corresponding to half of that value. The microwave system obtains discrimination and hence resolution by measurement of one or more of the quantities of light angle, the range, and the speed. So the angle is related to the beam pattern, right? Beam pattern, or the antenna pattern. So the angle. And the range is related to the time. It is really propagating perspective. So propagation velocity is very constant. And also speed. The speed means it's related to by the Doppler shift or the Doppler frequency shift. So we have three parameters to discriminate the objects. And so how is handled discrimination? It is defined by the beam width of the antenna. The beam width of the antenna is also defined or obtained by the peak, half the peak power response. So if the antenna has a narrower beam, the discrimination is batch coverage. So this is most of this area. And the resolution distance of ground is smaller. The range resolution or distance resolution is obtained through discrimination of the time delay. It is required to arrange discrimination because of the non-constant speed of the electromagnetic waves. Only the this is constant. Sometimes maybe in some years the propagation speed of the electromagnetic waves it varies, right, between different refractive index of materials of the mediums. So that means then the range resolution would be degraded, alright? And the third one is Doppler frequency resolution. And discrimination capability arises then because the received frequency is proportional to the relative speed between the object and the radar system. So here is a two-dimensional resolution. The first one, here, this area is the illumination area via the beam of the radar system. And there is only the angle here on this direction and on this direction, while the ATC coming via the pattern of the antenna. However, it will have a range. It's related to the time delay, alright? So it should along a circle with respect to this point along as here. So it's along this circle, the discrimination. It has the same time delay and it cannot be described. Alright, so here this is described the discrimination. This is the resolution range. And also for the Doppler frequency as we mentioned previously here. So let's along this direction. So in this range, this is the resolution range right here. However, if we combine the range resolution and the Doppler configuration together, become range Doppler. You can see our resolution area can become much smaller, right? So that means if we can combine the range and the Doppler configuration together, we can achieve a much higher resolution. So in practice, for an airborne or spaceborne radar, the range Doppler combination provides the best resolution. Since the half power Doppler response and half power range response contours may be made close together than the antenna beamwidth, the resolution obtained by combining range and Doppler techniques is really much higher than that obtained in angular environment ratios. So this idea is the basis for synthetic aperture radar and provides the finest possible resolution here. So, previously we introduced CW radar and a pulse radar, and the first radar is offer a better signal resolution for the than the CW because it can achieve it separates the transmitted signal and the received signal, and hopes that it could achieve there is no interference between those. So, however, the CW radar has no range but high discrimination regulations. Alright, so now if we still want to institute on the CW radar, use synthetic radar? How I will achieve a rate discrimination or the speed discrimination? Then we can use the FM synthetic radar. So FM means frequency modulation. The frequency modulation, that means the carrier frequency is not a constant, it varies. So here for this plot, you will see the carrier frequency varies between F1 and F2 and in a linear relationship. And the power speed in soil, or linear frequency modulation, LFM. So here, at the transmitter side, it varies our frequency from F1 to F2 linearly. With respect to time t, you see, it varies to F2, and then come back to F1, and then increases to F2, and then back to F1. Blue color line or blue color curve. Okay. Then at the receiver side, we have the received signal. That's the red color. So the received signal, you can see there is a difference, a time delay between both, right? So it is capital T. And also the TR is the modulation period. TR is the modulation period. And R is the slope of these lines. It is called ramp rate. So R1 is related to the modulation period, TR, and also B. B as the bandwidth, because it varies our carrier frequency from F1 to F2. So B equals 2 minus F1. The bandwidth of bench. So because they are always in a linear relationship, and the time delay divided by half of the modulation rate, the modulation period, equals Fi. Fi is the RF frequency, or the intermediate, and the intermediate frequency called is the difference at the point from this point to this point, not from F to F1, but from all the curves. So it is divided by the bandwidth, like that. So they have such a relationship, and then the Fi can be obtained by this right, by 4B divided by CTR times R, because T is a predetermined value. So it can be expressed by this term, R by the ramp rate and also the range between the object and the antenna, the radar system. So when we extract Fi from this curve, because it varies like this line. It varies like this one. You can see it's a periodic curve, right? It's periodic curve. So at the receiver side, from the measure Fi and then we can get information about the wind. So this kind of range discrimination. So how we can obtain Fi? So at the transmitted side, the spectrum like this one, but at the receiver side, it becomes this one. So from this one to this one, it is done conversion. So that's why, as we previously mentioned or introduced, at the receiver side, we should use a mixture, right? A mixture. A mixture can realize the non-conversion of the received signal to the baseband. And so this is how the FM radar system operates, and its range resolution is related to the bandwidth of that. So here, now we can change our range resolution by varying the bandwidth of the radar system. So that's why we want to use a wide bandwidth range for radar systems, because we can get a much higher range resolution for that. So the effective range resolution depends only on the bandwidth of the LFM CW signal. It does not depend on the sweep length. It only depends on the bandwidth. However, here we will just determine that the object is a stationary object. If object moves, we know that when the object moves, it is going to introduce a double frequency shift, right? Here, we just depend, this configuration depends on the frequency and the difference of the inter-IF frequency, right? But if the object moves, that means the frequency becomes the correct frequency times the frequency shift. So this value varies at the receiver side. The transmitter side is at 1 and 2 value. The receiver side maybe it becomes at 1 plus or minus something, and at 2 becomes at 2 plus or minus something. So it's gonna change, or it's gonna disturb the symmetry of this plot. So how is it? In this plot here, we can see the transmitted signal is symmetric, but the received signal, if there is double shift, you can see it varies, right? It is not symmetric. This is the shift routine. So, while varying the I frequencies, both the range and the radial velocity can also be determined by this one. So, it becomes like this one or this one. Without or with the double shift helps to recognize the momentum rate. For pulsed radar and radar, pulsed FM radar, that means, as we mentioned, its frequency varies, right? So we really use a chirp radar. Chirp pulse really looks like this one. Its frequency varies. So here, in a chirp radar, the transmitted signal is modulated in amplitude or frequency or phase, like this one. So the transmitted pulse looks like this one. It's bigger than this. From F1 to F2 again. And the received pulse also program back to if there's no, the object is not moving and there's no shape, alright? So we need, at which time we need to do this determining algorithm. The received signal by using a band pulse filter that has constant amplitude, but frequency varies with a time delay like the opposite to the transmitted pulse. So that means a compensation, right, to the transmitted pulse become the straight line. So, yeah. So, at the amplitude side, if the transmitted signal is square wave, the received signal is square wave also, after the determining, it becomes a sync function. A sync function. Yeah. So if we compare both, we know that after the determining, the amplitude of the signal is increased, but its bandwidth is decreased. Alright? Compare the square wave and the chart wave or the sync function wave. Its amplitude is increased, but its bandwidth is decreased. So we call this one as the compression. Algorithm called compression. So the effective width of the D-chart waveform is usually D over 1, and the compression ratio becomes T over tau over tau P. Tau is the pulse length of the transmitted pulse, right? Tau P is the compressed pulse length here. So the ratio between both is the compression ratio. It equals tau times speed. That means it is related to the transmitted pulse length and also the bandwidth. So J comp is called the gain because it is related to the signal noise ratio at the receiver side and with respect to that and the transmitter side. They're also related to tau times speed, the bandwidth. So for a radio system, we know how it targets, right? And the configurations for different requirements, and also if we want to use the radar to monitor a target, before we collect data that we want to get the information about the object, we need a radar calibration for that. Otherwise, we cannot get the accurate information about the object. So radar calibration is also a very, very important component of algorithm for radar systems. For radar calibration, there are internal calibrations and the out calibrations. Here for the internal calibrations, it may be used to calibrate the ratio between the transmitted signal and the received signal. So we can only use it to measure a ratio, not the exact value. One from less we can decide where. At the transmitter side, the transmitter, the radiated power is P naught T. So after a cover, there is a loss, LT, a loss factor. And also because part of it is the internal calculation means this is a chip inside of the system between the transmitter and the receiver we used. A configuration of a connection between the transmitter and the receiver to achieve this. So there are some calculations for the parameters that we collect, and finally there is relation between the previous determined value, transmitter receiver side, and detected value, and the ratio, a constant which is called overall calibration constant. So it is related to the parameters of our systems, such like IoT is the coupling loss factor, and the transmitter receiver side, LDCT and LDCR is related to the connection to the transmitter side to the emanation from the emitter to the receiver side. That is loss factors. So this is internal calibration. And also for noise measurement. So we want to erase influence the noises. How we do that? For example, we can do as we have two configurations and we will just switch in both. The top one, we take the information which only lead onto the noise because there are one part signal parts and another signal parts where we have time separation. And we can take an integration inside this time separation and just onto the integration of the noise and then the integration of the signal plus noise, and we use a subtractor both. It can only get the signal or only the power of the signal, and the noise, the power of noise is get rid of that. All we subtractors that we can also get if we set this is signal plus noise only and this is the signal only, and get all the noise. So this is for internal calibration. However, for external calibration, that means the transmitter and receiver is no communication between the transmitter and the receivers. We only use the objects outside of the system for calibration. So, for example, our illumination area, the blue color region, and our resolution area is this small area, and we choose the target, or we put the target inside of it. So the back reflection from target is used for the calibration. And here we need to know how the target is, and the calibration target is, and how the backscattering from the target is, and it can be used for the external calibration. So we really use several kinds of objects for external calibration. For example, flat rectangular plate is with a cross-section and expressed by this one in a collision coordinate system. And its maximum cross-section is this one in theta equals 0 and phi equals 0. And also we can use sometimes manospheres for that. So manosphere, its cross-section is really pi r squared. Is the larger than 3 minutes. Only the radius of the object is close to the limit or smaller than the limit, the extinction efficiency should be much larger. So this one. And remember spheres and corner reflectors. The high-angle corner and also high-angle corner reflections can be used for corner reflectors and also the triangle patterns from it is very wide. So it can achieve a very large RCS truncated triangle because from the corner of the reflection, it doesn't achieve a double reflection by the ground. We need one, we want to get respect, so we just choose the lead region. And the corner region cut off this kind of reduce. And this will not reflect the RCS, but it will reduce the possibilities of double reflections. And the rule frequency also is used for such illumination because it can focus a plane wave onto just one point. So the intensity is such white more.
Okay, see you guys.
Here is several times lenses and achieve very wide angle, so that such is the maximum RCS.
对着模板咔咔咔咔贴上去，咔咔咔，往这边上，然后把地方全删了，刚刚好。地方也不用，地方我都不会，哪里还没。